could cool itself, light itself, and make you feel comfortable, all while reducing carbon emissions.
I'm Peyton.
Hi, I'm Jamie.
Hi, I'm Sophie.
Hi, I'm Jasmine.
Hi, I'm Maria, and this is the breakdown of the Anita Lawerence Centre.
It's one of the most iconic buildings at UNSW. Designed in the 90s with passive systems, it still manages to stay smart, sustainable, and totally relevant. Let's take a look at what it's made of, and how those materials hold up today.
Passive design is about letting nature do the heavy lifting. Instead of relying on mechanical systems, it uses smart design choices, like thermal mass and cross-ventilation, to regulate indoor conditions. At the Anita Lawerence Centre, everything from the building's orientation to the materials chosen was done with intention. Sunlight warms, shading cools, and airflow keeps things balanced. And all this helps reduce the building's energy use and carbon footprint, which is crucial for long-term sustainability.
So Maria, what is this building made out of? It looks pretty indestructible.
Good question. Structurally, the building is built almost entirely from reinforced concrete, columns, beams, slabs, and core walls. It's designed to take on heavy loads and last a long time with minimal maintenance. Concrete is a load-bearing beast, but its environmental footprint is high. In the Anita Lawerence Centre, it's not just about structure. Concrete is used smartly for passive design. The thermal mass behind the terracotta absorbs heat during the day and releases it at night. Still, concrete production contributes around 8% of global CO2 emissions, which is why sustainable upgrades like SCMs and carbon capture are key. Steel reinforcement bars or rebars help the concrete withstand tension. Without them, it would crack under pressure. And check this out. Cantilevered slabs create overhangs for shade, while a hidden thermal mass wall behind the terracotta helps regulate internal temperature. So it's tough on the outside. Sophie, how's the inside?
This is where things get cozy. The non-structural elements are just as smart. You've got the terracotta cladding that doubles as thermal shades, louvers, both manual and automatic for airflow, carpet to insulate and keep it quiet, and acoustic panels in the lecture spaces that cut down echo. A nod to Professor Anita Lawerence, who specialised in acoustics. Non-structural doesn't mean non-essential. These features improve comfort and energy efficiency. Terracotta cools by shading, carpet reduces heat loss and echoes, louver windows provide cross-ventilation, acoustic panels create quieter study zones, especially important in a building used by over 3,000 students. Let's take a look at the non-structural materials, their properties, functions, and selection criteria right now. First, we have carpet. It's grey, insulating, and noise dampening. The carpet insulates the floor by trapping air within its fibres, creating a barrier that resists heat transfer. It provides comfort and reduces noise because of its cushioned and supportive surface, absorbing impact and noise. It helps enhance room aesthetics through adding visual interest, and helps to support thermal comfort as it retains warm air. Next, we have the glazed ventilation louvers and the glass louvers. They're opaque to avoid blind interfacing, and they have both automatic and manual controls. The louvers allow for controlled airflow through natural ventilation, maximising natural light. Their wind-driven stack ventilation is located centrally throughout the building, which enhances natural ventilation. The building has a focus on natural ventilation, and it's energy efficient as it's automatic. The terracotta facade is a flame red colour, highlighted by the sun because of its north facing. It's a collection of horizontal windows set deeply into the terracotta wall. The terracotta facade holds a symbolic meaning of uniting the International Centre, the School Faculty of Built Environment, and the School of Mathematics together. It accommodates 3 levels of academic spaces in a compact cellular configuration. It also provides shade for the concrete wall behind it. The terracotta facade is malleable and durable nature, which make terracotta ideal for shading. It's also minimal fire risk.
Ventilation system, vertical shafts. Mechanical system, metal material, lightweight, prefabricated steel ventilation shafts are used adjacent to complement the chemistry school machine aesthetic, enhances air circulation by facilitating movement of air between rooms and floors. These provide minimal background ventilation, which allows for fresh air, supports the building's passive environmental system, and improves energy efficiency.
Acoustic panels. As part of their properties, they're used in lecture rooms and studios to help manage sound. As baffles, they are hung from ceilings, and as wall panels, they add a decorative or aesthetic element. As baffles, they function by absorbing sound and reduce reverberation and echoes. Part of their selection criteria is because they're used to optimize working space, minimizing distracting noises.
Exposed thermal mass and soffits. They are heat absorbent, made of concrete, and integrated into the walls. The exposed mass in walls and soffits is used to absorb heat during the day and release it at night, helping to regulate internal temperatures, and it manages reverberation. It also helps regulate temperature. Concrete is used due to its high thermal mass and is effective in absorbing heat.
So Jamie, how sustainable is the terracotta?
Terracotta is a passive design dream. It's long-lasting, low maintenance, and recyclable, but it's made in superheated kilns powered by fossil fuels, and that's where emissions spike. Solar kilns are a cleaner option. They run on sunlight, and Australia has plenty. Swapping energy sources could reduce emissions and even improve safety in production.
Terracotta is low maintenance, long lasting, and helps regulate temperature. But the catch? Its firing process. Traditional kilns rely on fossil fuels and can burn for days at over 1,000 degrees Celsius. This accounts for over half the energy use in ceramic production. Solar kilns are a cleaner, more modern alternative. They rely entirely on renewable energy, are already being trialled globally, and could be a game changer in countries with strong solar potential like Australia. Adopting solar kilns would dramatically reduce the environmental impact while improving safety and costs long term.
And concrete?
Concrete is essential for the building. But it's also one of the most emission-heavy materials. Cement production alone contributes to around 8% of global CO2 emissions. Concrete is everywhere, but so are emissions. That's why alternatives matter. SEMs like fly ash and slag reduce the amount of cement needed, cutting emissions by up to 45%. Renewable powered cement plants and carbon capture tech are being piloted globally, and new materials like self-healing concrete limit the need for repairs. Even recycling concrete helps by cutting waste and keeping materials in circulation. There are sustainable options though, using fly ash or slag instead of 100% cement, switching to solar-powered cement plants, using carbon capture tech, and even self-healing concrete that repairs its own cracks. So, why did concrete cross the road? To reduce its carbon footprint.
The Anita Lawerence Center isn't just a building, it's a lesson in sustainable design. Materials like concrete and terracotta work well, but with a smarter manufacturing process, they can do even more. Whether it's solar kilns or green concrete, the future of construction is all about reducing impact while boosting performance.